So if a function levels off to some kind of limit, as happened in two of our three previous examples here, then that's a horizontal asymptote for the graph. That's what a horizontal asymptote is. It's the end behavior of the function if it levels off to a numerical value. So in the first case, this rational function here had a horizontal asymptote at 1/4. This one had a horizontal asymptote at 0. The last one did not have a horizontal asymptote at all. So most rational functions, in fact, pretty much all rational functions, polynomial over polynomial, whatever the horizontal asymptote is from one side, it'll actually be approaching the same thing. So if we had taken those problems from earlier again and went back and looked at this limit here as we go to negative infinity, we also would have gotten 1/4. If we'd have done this one going to positive infinity, nothing about this problem really mattered whether it was positive or negative. We'd have also approached 0 from going to negative infinity. But now we're going to look at an example of a function that actually has two horizontal asymptotes. And it's actually a function that involves a radical. So 3x minus 7 over the square root of x squared plus 3x. So we're going to begin by looking at the limit as we go to positive infinity and see what that approaches. And then we'll turn around and look at the limit as we go to negative infinity. We're going to see that it actually approaches something different. So we begin by taking the limit of this thing as it goes to infinity. And then we use the shortcut to kind of break things down idea that the dominant term in the top will determine what the top does. So that's a linear polynomial. So the dominant term is the 3x. So that's going to decide where the top goes. The bottom, you have a square root, but inside that square root, we have a polynomial. And we know the polynomial is going to be dominated by its largest term. So in terms of a limit going to infinity, all that really matters here is square root of x squared. So we have 3x over square root of x squared. We just need to simplify that and see what happens. Well, very important idea. Remember, square root of x squared is absolute value. But absolute value is equal to just x when x is greater than or equal to 0. That's the definition of absolute value, or part of it anyway. So that square root of x squared in this problem can be replaced with just x. And so we have limit as x goes to infinity of 3x over x. The x's cancel out. Limit of a constant would just be 3. So we have one horizontal asymptote here at x equals 3. And then we turn around and say, well, what about a second horizontal asymptote? Is it possible to have a second one? Yeah, it is. Yes, it is. And so we look at it as we go to negative infinity. And in this case, we're actually going to get something different in this problem. Because the setup's the same. We have the limit going to negative infinity of 3x minus 7 over square root of x squared plus 3x. So we reduce it like we did before, saying, well, again, it really only matters what the dominant term in the top for a polynomial does and what the dominant term in the bottom does. So that's 3x over square root of x squared. But remember, square root of x squared is absolute value. When x is negative, absolute value can be replaced with negative x when x is less than 0. So therefore, we have the limit of 3x over negative x. We simplify, the x's cancel out, and we get negative 3. So this function has a horizontal asymptote at negative 3 and at 3. If we look at a graph of this function, 3x minus 7 over square root of x squared plus 3x, we can see here that we have an asymptote there when that stuff in the bottom is actually approaching negative values at 0 and at some other place, which we can't really work out here from the graph. But what I want you to really see, the whole main purpose of looking at the graph is to see that on the right-hand side of the graph is closing in on positive 3. And on the left-hand side, as we go to negative infinity, there it is approaching its other asymptote. So you can see that we do have two different horizontal asymptotes. Now, this rational function isn't the only situation that you can encounter where right and left are different. So you might recall our good old friend y equals e to the x. Y equals e to the x. It has a horizontal asymptote at 0 when x is going to negative infinity, but it goes off to infinity on the other side, so it doesn't approach any kind of asymptote over there. And the last function, one that you might have talked about previously in a math class, is what's sometimes referred to as a logistic curve. And that also has two different asymptotes. Usually at 0, you go far to the left, and then your maximum capacity, which in this example is 10. This is called logistic growth. You see this in some populations where there's some limit on the amount of resources available. You have this kind of behavior. You'll also see it if you do titration curves in chemistry. You'll sometimes see this S-shaped curve. You also see it in psychology. This S-shaped curve is sometimes referred to as the learning curve. You start learning very slowly with a new topic, then you have kind of a growth spurt, then it kind of slows down your learning, and at some point you kind of learn a lot, and then you reach a plateau. And what really happens in reality is learning continues like that over and over, multiple S-shaped curves. And you can actually get that kind of behavior with titration curves as well. If you ever look at titration curves with pH for different solutions in chemistry, if you do that in a chemistry lab. Okay. So those are some situations in addition to the one we just looked at where the horizontal asymptote behavior is different on the two sides.